Hello, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Jacob Hendrickson. Jacob started as a thermal EOIR engineer with Thermal Analytics in June of 2020. He creates thermal models for military and commercial contracts using Pytherm, MuSES, and Cotherm. These models are frequently used to generate. Other technical efforts of Mr. Hendrickson involve human thermal modeling, software training, facilitation, and support, and software development support. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar, and we'll be sending you the link following this presentation. And with that, Jacob, if you're ready, you may begin.
Thanks, Chris. Good morning, everyone, and thanks for taking the time out of your day to join us for the Aircraft and Drone Capabilities webinar. I'm Jacob Hendrickson, a thermal/CFD engineer with Thermal Analytics. In this webinar, I'll be discussing how to best use MuSES for airborne target modeling. In this presentation, I will talk about the motivation behind airborne target modeling, give a quick introduction to our software MuSES. Then I'll describe the airborne target model creation process, including modeling weather at altitude and aerodynamic convection application. After covering the basics of the airborne target model creation process, I'll talk about importing CFD plumes into the target along with hard body considerations when incorporating plumes into a model. After plumes, I'll describe the sky modeling and atmospheric effect options available within MuSES, including use of an image compositor. Finally, I'll describe some example airborne target models previously created by Thermal Analytics, and then I'll end with talking about future work and advanced applications. The motivation for this webinar is to demonstrate MuSES's capabilities for modeling airborne targets, both thermally and within the EOIR spectrum. For signature and IO solutions, MuSES can simulate any environmental condition and generate accurate thermal signature predictions of your aircraft system. A custom convection code built into MuSES allows you to understand fluid flow surrounding the wings at high altitudes and during fast travel, which we will discuss later in the presentation. Relevant concepts relating to airborne model attribution and creation will be introduced and discussed to provide a groundwork for airborne target modeling. Once that groundwork is set, I will discuss the key aspects that are critical to creating an accurate thermal prediction. In the same respect, care also needs to be taken when setting up and creating 2D sensor renderings in order to produce accurate synthetic IR imagery. Finally, the methodology of airborne target modeling within MuSES will be described with detailed examples. To start, I'll give a quick overview of what MuSES is and how the software functions. Our flagship software, MuSES, is a thermal solver and infrared rendering program, which takes inputs such as a 3D CAD geometry description, part material thicknesses and thermal properties, and component heat sources, as well as boundary conditions such as the sun location, the sky, and the background for radiation exchange, air temperature, and speed for convective heat transfer to properly set up the analysis environment. Once these are combined, we get a physical temperature prediction of the target. Sensor images, which can be specular or diffuse, as well as spectral or across a broad band. And we can also get contrast metrics such as delta TRSS and contrast radiance. Being able to gather all of this information from one software is what helps make MuSES such a powerful tool for those who care about the IR spectrum. Now we can describe what makes airborne target modeling different compared to ground vehicles. Now that we have a base understanding of how MuSES functions, we can start to understand how airborne target assets are modeled within MuSES and the different aspects you have to take into account when your target is off of the ground plane. Throughout Thermal Analytics history, we have developed an extensive model database. This database includes a sizable collection of airborne targets. Helicopters, commercial jets, fighter planes, and drones have been fully characterized and are ready for simulation. So we have extensive experience modeling these types of assets. Our target library also includes tracked and wheeled ground vehicles of different uses, maritime targets of multiple sizes, and personnel in numerous poses. If any of the models here interest you, or you are interested in a full target model library, please contact your account owner and they would be happy to send that information to you. As the weather and atmosphere change with increasing altitude, the physics and modeling assumptions made for ground target modeling will need to change for airborne targets. As the altitude increases, the lapse rate and relative humidity varies depending upon which portion of the atmosphere you are currently traversing, while the pressure decreases with increasing altitude. Because these values vary with altitude, we need to account for these changes within our thermal model setup by correctly modeling the weather at high altitudes. Fortunately, MuSES allows us to model weather at altitudes other than ground level. We can do this by specifying an additional at-altitude weather file, selecting a built-in standard atmosphere, specifying a custom atmosphere profile, or using the information contained in the ground level weather file. Moving forward, models shown will use the atmosphere profile option. This option must be selected for aerodynamic convection, which is used on the airborne target models. The University of Wyoming radio sound data is a good source that can be used for acquiring this type of data. As a basic introduction, aerodynamic heating is caused by kinetic energy being converted to heat when the velocity of a fluid slows down relative to a surface. Heat is generated in two primary ways: at stagnation points due to compression and along a surface due to friction. We'll dive into a bit more detail in the next slide. As mentioned, aerodynamic heating results from a fluid passing over a solid surface at high speeds. This causes forced convection where a flow field is created by these forces that are beyond normal thermal processes. When air flows over the surface of an object, the molecules closest to the surface stick to it. This is called the no-slip condition, where the velocity at the surface is zero. The next layer of air above slows down due to friction caused by colliding with the air molecules next to the surface. These slower moving molecules then collide with the next layer of air above, and so on. As you move further from the surface of an object, fewer molecules are affected by collisions until the free stream velocity is reached. This is so far away from the object that the flow is completely undisturbed, and so the velocity remains constant. This creates a thin layer of fluid near the surface where the velocity of the fluid changes from zero at the surface to the free stream velocity. This thin viscous region of air's flow is called the boundary layer, and it is the main source of friction drag on an aerodynamic body. In most cases, the boundary layer is very thin compared to the rest of the flow, but it can have a significant effect on the aerodynamics downstream. As we know, energy is conserved, and when these air molecules slow down, that kinetic energy is converted to heat. A few other things to note. Temperature increases with cruising speed because the relative motion increases, and the difference between the zero and the free stream velocity is greater. Temperature also decreases with altitude because the air is less dense, meaning there are less molecules to collide and create or exist in that boundary layer. Because of high speeds, it is critical to consider aerodynamic heating at supersonic speeds. Let's take a look at how we can do that within MuSES. MuSES has an aerodynamic convection library that supports both airfoil and nose surfaces. Heat transfer phenomena for high-speed flow around such geometry are modeled using convective correlations from published research. These correlations are based on a normal vertical shock wave ahead of the stagnation point. To help determine the appropriate flow correlations, MuSES uses fluid temperatures, flow speed, and altitude inputs for all airfoil and nose surface types. However, some surface types have additional inputs as well. On screen here, I have a model of a fighter jet that I'll use for demonstration in the next few slides as I discuss what those inputs are and how MuSES uses them. Computing aerodynamic heat transfer coefficients for airfoil geometry begins with determining the Reynolds number and the Prandtl number at a reference temperature to characterize the flow. A distinction was made between the body and the leading edge based on distance from the stagnation point. From there, the correlations depend on the flow regime. The Nusselt and the Stanton numbers are used to calculate the heat transfer coefficients. MuSES requires a leading edge diameter and element IDs as input for airfoil convection so the solver can distinguish between leading edge elements and body elements. MuSES can model flow around nose surfaces that are blunt, conical, or spherical. The shape is primarily determined by the application. For example, a blunt nose is sufficient for minimizing drag on a commercial subsonic craft, while a supersonic jet would require a sharper, more conical nose for minimal drag. The shape of the nose would change how MuSES determines which elements belong to the leading edge and the body. In any case, the starting point for the nose convection is the same as for airfoils in MuSES. It begins with characterizing the flow with the Reynolds and the Prandtl numbers. Again, the calculations and correlations are then determined by flow regime and nose shape. Here, we see a fighter jet using aerodynamic convection on every exterior surface. Notice that the heat transfer coefficients are highest at the stagnation points and decrease with distance. Now we've set up weather at model altitude and aerodynamic convection. We can run our simulations, evaluate design changes, etc. Comparing the fluid temperatures between the MuSES aerodynamic convective heating, which is shown on the left, and a star CCM plus computational fluid dynamic, or CFD simulation on the right, both images are using a 0 to 90 degrees Celsius temperature scale for ease of comparison. As we can see, there is a very good match between the two models. The main difference being that the MuSES version requires no CFD expertise to include in the model and is calculated much faster than running a separate CFD analysis. In addition to aerodynamic convective heating, we can also go a step further and incorporate other effects that improve the IR signature accuracy. One such effect is an exhaust plume. For some aircraft, the exhaust plume can appear very hot, especially to a mid-wave infrared camera. For these vehicles, it is important to include the radiance from the hard-body surfaces as well as the hot exhaust gases. The MuSES plume module incorporates the radiance of the exhaust plume along with the target hardbody to provide more accurate signature renderings. The images shown at the bottom of this slide are real-life examples of aircraft plumes using different IR sensors. MuSES can model exhaust plumes for added signature accuracy. Oftentimes, these plumes can be hotter and or larger than the hardbody target, so ignoring it can underestimate the overall signature. To do this, MuSES imports volumetric CFD results from an external CFD analysis tool, and will calculate the plume radiance when creating rendered images of the target. This plume radiance is only calculated for ray tracing paths between the scene and the sensor which pass through the area of the imported CFD results. We also support the inclusion of CO2, H2O, and carbon soot as species within the plume. In addition to plumes, CFD results can be imported to capture other interactions between the plume and the hardbody. Let's take a look at some additional hardbody considerations. I've discussed capturing aerodynamic convective heating using the aerodynamic convection library in MuSES. If desired, we can use CFD tools to help us capture other phenomena such as hardbody exhaust plume interactions. There are two main methods for applying aerodynamic convection to an airborne target within MuSES. The first is the built-in aerodynamic convection library, which is a simplified approach and is a fast way to get convection on the outside of an aircraft. But in the case with the image shown here, the exhaust gases are being forced downward from the force of the rotors and are impinging on the side of the helicopter. The best way to account for this phenomena is to include a CFD airflow prediction in the model. There are two primary use cases for importing CFD into thermal models. The first is to capture how an exhaust plume impinges on a hardbody, and the second is to account for the exhaust plume radiance as seen through an IR sensor. Moving from left to right, complexity is added to the simulation via inclusion of a plume and hardbody impingement. The left image is just the target asset with no plume radiance or hardbody impingement. The middle image shows the inclusion of a CFD plume radiance in the rendering. The downwash caused by the helicopter can now be seen. And the right option includes both the CFD plume and its hardbody impingement on the target. The downwash can be seen along with the exhaust impingement on the target hardbody. Now that we have discussed aerodynamic convection and plume radiance and impingement, next we will talk about modeling the sky background. Last but not least, I will describe how MuSES models the sky and atmosphere and how you can customize the settings to fit your desired airborne target scenario. I will now describe the different components that affect the radiance of a target within a natural scene. The first radiance source is emissions from the target, which are based on the physical temperature and spectral emissivity of the object. Next is energy reflected from the target of the surrounding terrain and objects. And finally, there are reflections of the sky. During the rendering process, MuSES also calculates the atmospheric attenuation between the sensor and the target, and for the reflection paths between the target and the surrounding terrain. MuSES uses the atmospheric transmission code MODTRAN for these calculations. MODTRAN is developed by Spectral Sciences. Within MuSES, the sky radiance is calculated using MODTRAN at many hemispherical positions to form a sky dome. The target view factors are used to interpolate from this sky dome and is used for background reflections and for rendering the sky in the field of view. MODTRAN calculates clear and cloudy sky radiances for each position of the hemisphere, and these radiances will be mixed for partially overcast skies. Extinction and path radiance are incorporated into the rendered radiances by modifying the source radiance values, which include the impact of atmospheric propagation path between the sensor and the scene. As source radiance is defined in MuSES as the emitted plus reflected radiation at its source, the propagation path between the source and the sensor modifies the radiance due to atmospheric effects. The result of adding atmospheric effects can be seen here, with the left image showing no atmospheric effects along the target sensor path, while the right image includes absorption and path radiance atmospheric effects to the sensor. MODTRAN inputs to control atmospheric effects can be controlled directly within MuSES. The primary way to interact with how MODTRAN inputs are selected is through the weather dialog box within the rendering settings. Within the weather dialog, there are several sub-tabs that allow you to customize the weather further. The first sub-tab, Clouds, controls which cloud model the simulation will use. The opaque cloud option assumes that the clouds are blackbody emitters at the altitude-dependent air temperature. This is an appropriate assumption for the mid-wave and long-wave thermal wavebands. The translucent cloud option is necessary for the shorter wavelength bands, like near IR and shortwave IR, where the cloud radiance is dominated by reflected and transmitted light, not temperature. There is also an option called direct beam scale factor, which controls the percentage of solar or lunar source allowed to pierce the cloud cover. Next, the atmospheric profile tab is used for defining the altitude characteristics of the atmosphere for your simulation. Upper layer humidity and temperature can be specified here, along with the inversion height above sea level, which controls the altitude at which air temperature begins to increase with altitude. The next tab controls the aerosol model used within the simulation. There are several different MODTRAN models to choose from in the drop-down list. These aerosol models are used for attenuation and path radiance calculations based on the scenario of interest. Each model has a default visibility which can be overridden by the user if desired. After configuring the weather to fit your simulation needs, the sky itself can be customized further. Users are able to control how the sky in the field of view is calculated and interpolated for rendering. Two sky dome interpolation algorithms can be chosen between. Robertson, which is good for long wave but poor for visible through near infrared, or cubic spline, which is more accurate in all cases and is the only appropriate choice for visible or near infrared, but may take longer to render. Additionally, users can control how sky radiances for target reflections are calculated and interpolated for rendering. The two options to select between for the sky reflections off target are uniform sky, where a single sky radiance from the thermal solution is used, or directional sky, where MODTRAN is used to populate the sky dome for interpolation. MuSES offers some flexibility on the amount of detail used in a scene simulation for both the target and the background. The default uniform sky background can be used, which is seen on the left image. We can change how the sky radiance is calculated by using a variable sky model as seen in the middle image. Other phenomena such as cloud cover, sensor blur, atmospheric humidity and temperature, visibility range, and atmospheric scattering and reflections can be incorporated into the simulation. This can be seen in the right image. We can also add a faceted or textured background plane below the airborne target. Composite imagery can also be created where we combine a radiometrically calibrated measured image with a simulated target. Clouds are not visible in MuSES renderings due to it using a mathematical model of cloud cover that averages the cloud cover across the entire sky hemisphere. To see clouds or other background clutter, we can create a composite image inserting a rendered target into a radiometrically calibrated measured image. Images on the top show a simulated commercial drone against a measured sky background with some cloud cover, with and without trees in frame, while the images on the bottom show a BTR-82A inserted into two measured scenes. Within thermal analytics, we have numerous projects that can highlight the capabilities of MuSES with airborne targets. Throughout this presentation, we've focused primarily on large manned aircraft, though we have experience with small unmanned systems as well. Thermal analytics has a fair bit of experience modeling UAVs, both big and small, battery-powered systems, or internal combustion-driven engines. Although it is a challenge to model these assets, we've created a repeatable target modeling methodology to account for the key signature drivers of these systems. Here, we're showing a larger UAV with the CH-4, which has an internal combustion engine, a battery-powered Skylark model, and two more commercially sized quadcopters, the Mavic 3 and the NX-110, which are also battery-operated. So let's first review the Skylark drone. To model this asset, let's walk through an overview of modeling details we need to capture in order to represent the airborne phenomenology as accurately as possible. We have a battery-powered UAV, and we've got a variety of airfoils, some fixed, some rotating. It has a battery pack with cells shown in the translucent gray image on the right, and we're indicating that we've got a rotating propeller on the front at a specific RPM. We've got a motor nearby that's geared to the propulsion component spinning the prop. The drone is moving at 50 kilometers an hour at an altitude of 1,000 meters. We have some heating in the sensor area, and again, the internal battery pack is denoted, as well as different surfaces experiencing aerodynamic heating on them. As mentioned, it is important to incorporate aerodynamic convection on a moving aircraft, and that convection impacts both fluid temperature and convection coefficients that are going to determine the heat transfer on the exterior of a UAV like this. So here we're focusing on the fixed wing and tail, the conical nose cone, and the rotating propeller. Highlighted on the right are the parts we've set up with aerodynamic convection, taking into account the leading edges and stagnation points necessary to calculate the proper convection and fluid temperatures for this scenario. And those edges and points are conveniently outlined in red within the MuSES GUI. If we run our scenario, those highlighted parts will experience aerodynamic convection for the duration of the simulation, which will impact the physical temperatures of the asset in the appropriate fashion. Here, if we look at the convective coefficients and the fluid temperatures experienced by the prop, we see high convection coefficients where the prop is rotationally cutting through the atmosphere and a small bump at the stagnation point on the nose cone. We see friction effects of the rotation at the tips of the prop where the rotational velocity is at its peak. Likewise, we see increased convection on the fixed wing and tail sections as well, which in the end will make the target signature physically realistic when we render an image. We also have several SUAS target models, which are small unmanned aircraft systems, and that is just any unmanned aircraft weighing less than 55 pounds. In this case, the NX-10 quadcopter follows the same basic concept as the Skylark. We've got an internal battery pack powering the unit and also generating some waste heat. We're accounting for some heating from the sensor in the sensor bay and some motor heating happening inside the gearbox, which is spinning the attached rotors at about 4,000 RPM. We're also applying aerodynamic convection directly to the rotor wings during flight. Again, the blue highlighted parts on the right are set up this way, with the leading edge of each rotor wing accented in red. And in this scenario, the drone is moving at 43 kilometers an hour at an altitude of 200 meters. Now we'll show a few rendering examples of UAVs and the type of sensor views MuSES can produce. On the left, we're looking at the CH-4 drone against the sky, and on the right, it's out in front of a cluttered background, more specifically a textured rock cliff in a canyon. Next, we will look at a drone swarm example using 3 Mavic 3 drones. The left image shows a ground-up swarm rendering example, while the right image shows a top-down overhead persistent IR rendering example against the textured terrain background. Next, I'll quickly describe a few areas of interest we began researching internally. Aircraft countermeasure flares can have a large impact on the overall signature of an aircraft. There is an ongoing effort to characterize and simulate these countermeasure flares, which is already showing promising results. As seen below, there is a mid-wave IR image of the countermeasure flares in progress, along with a video showcasing the capability. Currently, MuSES can model objects moving at subsonic and supersonic speeds. Internal research is being conducted into expanding the capabilities to include hypersonic objects. MuSES currently supports 3 plume species, carbon, CO2, and H2O. We have an ongoing research effort to investigate expanding the number of species that MuSES can support. Throughout this webinar, we have seen that using MuSES, the user can model high-value airborne targets across the infrared spectrum. We have talked about how MuSES can accurately model different aspects of airborne target modeling, such as aerodynamic convective heating, along with incorporating volumetric plumes into the model. And finally, the simulation accuracy of airborne targets can be enhanced by including appropriate sky, atmosphere, and background settings to replicate real-world phenomena that would be seen by a sensor. Thank you for taking the time out of your day to attend this webinar. I can open it up for questions now.
Thanks, Jacob. So yeah, let's get to some questions. First one here. Is ModTran included with MuSES?
Yes, ModTran is included when you purchase a license of MuSES.
Perfect, thank you. How can I create my own composite imagery?
Currently, we have an internal tool for creating composite imagery and are currently working to convert that into a Kotham process that would be shareable with the public. So stay tuned for more information there.
Okay, thank you. What range of Mach numbers are valid with aerodynamic convection library?
The aerodynamic convection library supports any Mach number below Mach 5.
Okay. Let's see, got one more coming through here. How big was the terrain file size in the UAV example slide?
I believe the background below the CH-4 was around 800 meters by 800 meters. Though we've made terrain bigger than that and smaller than that before.
Okay, thank you. Looks like that's it for questions. So that will complete today's webinar. We appreciate you all attending. You will receive a follow-up email containing links to download the presentation slides and watch the recorded webinar session. Again, thank you all for attending. Everyone, have a nice day.
Thank you.